Hello, everyone. This is the second in a series of lectures covering Chapter 17. Today we'll be talking about the section 17.2. So, when we talk about the speed of waves, we've seen that it usually comes down to some ratio of a term relating to how stiff a spring is or how tense a string is over some term related to mass. And for the speed of sound waves in a gas, the formula is the same. So if you want to calculate the speed of sound, say in air or any other gas, you need to first know the bulk modulus of that gas as well as its density. So knowing both things, then you just take the square root of one over the other and the square root, and I'll give you the speed, which of course it's constant, like wave speed on a string. The bulk modulus, it's a term that comes from statics, so it's more to do with the mechanics side of physics, where it measures effectively how stiff a gas is, how much it resists a change in volume as you apply a pressure on a gas. So how hard is it to stretch or compact, or stretch or squeeze a gas? And the units of that is the Pascal, or newtons per meter squared. So it's a measure of how much pressure you need to apply to cause some stress on the gas. And this is a lot like the speed for waves, because you're taking a ratio of the tension over the mass density. You're kind of doing that but in 3D for the gas, where now you're taking that term here, rho, which is the cubic density, for a three-dimensional gas taking up, all space. So the general idea then for calculating wave speeds is that you're always taking a square root of some elastic property of the medium over an inertial property. So the elastic property, right, tends to make for faster mediums the more elastic a medium is, because think of this like this elastic property is your spring constant. This is the tension on the string. This is your bulk modulus. This is essentially how stiff something is, and as such, the more you displace that from equilibrium, the more it wants to fight back and get back to equilibrium as soon as possible. Then there's this inverse proportion with the inertial property, because that tells you how much mass is there, how much is getting in the way, how much needs to be accelerated to get some speed going. So the more of an inertial property something has, so it's more dense or has a bigger linear mass density, then the harder it is to get it going, to get up to a decent speed. So for gases, then we can use this formula and figure out the speed of sound through any gas. Though for liquids and solids, it's a slightly different formula, but again, similar idea of using a modulus and density, but we'll mostly work with the gas formula here. You can find for various common media what the speed of sound is through all of them. And you'll note that the one you probably know well is the speed of sound in air, 343 meters per second at about room temperature. It's a lot faster, though, if you look through the columns. The air speed of sound is actually pretty slow compared to sound through liquids, and it's even faster through solids. The reason this is simply because solids having more particles are also more stiff, and as such, they are able to essentially have a stronger sort of restoring force when they vibrate, that makes them move back and forth from their little equilibrium positions a lot faster than in air. So the max change in pressure then is actually related to the bulk modulus, which again is a measure of how much stress you can put on a gas before it starts to compress or expand. So based on that, there's a relationship then between how the gas changes in pressure and its bulk modulus. So you're able to talk about the max change in pressure as a wave passes through a gas in terms of its modulus, and you can also do it in terms of its density and its maximum displacement of any element of the gas. So there's two ways here to talk about it, either if you know the bulk modulus and the wave number, or you can just talk about the density, wave speed, angular frequency, and max displacement for the sound wave. Now, there's actually a functional relationship for the speed of sound in air as a function of temperature, and it's this right here. So this kind of shows you how the speed of air increases, sorry, the speed of sound in air increases as the air temperature increases. So the term here is for the air temperature in Celsius, effectively as warmer air acts as a better medium for the warmer air acts for a better medium for waves to propagate through. And the idea too is that essentially, right, as the air gets hotter, it gets less dense. So you remember the relationship between speed of sound in the gases and the density, and then the density decreases as air gets hotter, then speed increases. So you can use this formula. It's calibrated though to get a value of 331 at temperature of 0. So if you plug in the room temperature 20 degrees, you get the classic speed of sound in air, 343. And something cool is that whenever you hear lightning, you can actually measure how far away the lightning is based on how much time passes between the lightning and hearing thunder. Since the speed of sound is about 1/3 of a kilometer per second, then that means that it takes a sound wave 3 seconds to travel a kilometer. So you just need to see lightning and count the seconds between that and when you hear thunder. Every 3 seconds that pass between the lightning and the sound of thunder means that the sound wave has traveled 1 kilometer. In other words, if you see lightning and then you hear thunder 3 seconds later, it means that the lightning bolt struck 1 kilometer away. If you hear the thunder 1 second after lightning, then the thunderbolt struck about 1/3 of a kilometer away from you, and that means it's pretty darn close. And that's all for section 17.2. I hope you join me next time, where we'll be talking about what will we be talking about? Oh, that's right. We'll be talking about the intensity of waves. Hope to see you next time.